Hello there, and welcome to Network Wednesday here on Ants Are Everywhere. Today, we're going to take a look at the source code for IP filter. Let's try this again. Hello, and welcome to Network Wednesday here on Ants Are Everywhere. Today, we're taking a look at the source code for Iptables, the firewall utility for Linux. Iptables is brought to us by the people at netfilter. And it's not the most recent, most suggested way to configure your firewall on Linux. The more up-to-date thing is to use nftables, but Iptables seems simpler. It's still used widely, and if I understand correctly, under the hood, if you have an up-to-date recent Linux system, then really the tables are or the rules are being written as nftable rules, with Iptables kind of being a sort of backward compatibility mode. So just for the sake of doing something that's a little bit simpler than nftables in our first go around, we'll look at the more classic Iptables implementation. Here's their website. They list their features and whatnot, and I guess let's talk a little bit about what we expect to see. So it's a firewall. So at least the firewalls I've configured, I don't know if I've ever used Iptables directly in a way where I really understood what I was doing. But there are all sorts of ways to configure firewalls. And typically they have a set of rules. And essentially there's going to be some structure that has the rule implementations, and when you get a packet, there will be some matching operation. And if something, we're going to walk along, essentially, presumably some kind of array or collection of these rules, see which ones match, and if they match, apply them kind of in order. So that's the sort of thing we expect to see. Those are the data structures and the algorithms that I'll be trying to find as I look through the source code. Here's Iptables, the official Git repository. I think this is cgit. I'm not 100% positive. We looked at the Git source code yesterday. I don't see what looks like an authoritative Iptables mirror. So I'll try browsing directly on this interface, and then fall back on Emacs if it seems like this is not working for us. Okay, so here's the Iptables master tree, and let's see, what do we have here? We've got a few folders. Etsy should be like etc., extra configuration-y stuff, maybe utilities. Extensions is presumably ways of extending Iptables. Include will be includes. This might include some of the more important like C headers. So we'll open includes. And then we've got this lib IPQ, lib IPTC, lib Xtables. I'm not sure what these are, but maybe they're important. And we also have Iptables, which was the first, which was before these. And then M4 should be macro stuff, utils is utility. And we have a single Iptables test.py, which I guess we might as well look at. Let me break out these AI assistants into their own window. Okay. So here we are. So this is include. Let's not go to include here yet. Here's the Iptables test. And we do not get syntax highlighting. Is that a deal breaker? That might be a deal breaker. But let's see how far we can get without it, since this is just a test. We get a run test function, which is going to take some Iptables, a rule, but we get parameters. Okay, so a string with Iptables arguments for the rule to test. Rule save, define the rule in the output of Iptables save. And res, the expected result of the rule. So I guess this, you'll say if I block this thing, then the result should be it's blocked. And then I guess the test will return true or false, essentially, fail or not fail. And a file name for the file to be tested, a line number being tested. Maybe this is for line numbers in the iptable source code. Yeah, okay. So when we call run test, we're going to tell it the file that we're testing, which might be like foo.c, and I guess we'll tell it we're testing line 100. And then we have something for network namespaces to call. Okay. And it's going to call execute command. Let's see what execute command does. So this is going to execute the command, checking for seg vaults and returning the command exit code. Yeah, okay. So it's just going to call out, I guess, to the shell, right? We're going to check if it starts with IP tables or IP6 tables, or ends with EB tables, etc. I guess ARP tables is maybe IP tables for ARP. And okay, so we're just calling subprocess calls. So we're calling a shell, essentially the IP tables shell command. And then presumably we should generate traffic, right? Check for sig vaults. Yeah. But where is the, how do we know if we've blocked stuff successfully? I don't know. It seems like this is just testing whether the command itself succeeds. Okay, so let's, wait, what is this function here? Run test file fast. Run a test file, but fast. Okay. And then maybe there are, here's spawn net ends. This looks promising. Prefer unshare module, import unshare. Okay. Sledgehammer style. Call ourselves, prefix by unshare. So we're going to try to import shutil. Now, I don't know what unshare is or shutil is, but we're going to exec v unshare. Let's see what unshare is. We have a Linux man page. Run a program in new namespaces. So this is running a program, I guess, in some namespace. Okay. And then we have a main. So I'm going to guess that somewhere that they're going to actually, so this is just a test runner, right? So somewhere there must be tests. And maybe xlate test is important. Maybe not. This is translate test. Okay. So I'll keep an eye out for tests as we're going through. So here we are in the include, and we get the IP tables headers. And here's the source of the IP tables directory. And we get, let's see, we have IP6 tables and ARP tables. Save and restore .8. I'm not sure what that is. We have some sort of XML stuff, XML in. We have some C files. XSLT. Look up XSLT file extension. Which provides rules that an XML file should follow. Language transformations. Okay, so some sort of language transformations for XML. And then we get a bunch of C files and H files, including some stuff with X tables. Okay. So I'm curious what these save and restores are. These might, let's find out. This is a man page. Okay, maybe this is like, okay. All right, so .8 seems to be a man page. What is .in? This is also some sort of man page. Yeah, this is some sort of help or man page, it looks like. Okay, cool. We should look at a bunch of these files. I guess I'm going to jump to Emacs soon. I think this was the only, did we look at libpq, IPQ library for user space? Cool. And then libiptc Linux. I wonder if Linux is important. Oh, we're still going to include here. Libiptc, a library which manipulates filtering rules. Okay. I'll just do a web search to see what I can find about libiptc. So it seems to be maybe part of Iptables as opposed to something like third party that they're including. All right. And then we have netfilter stuff in include Linux. So netfilter, I think, is this thing that's going to interface with the Linux kernel, which would make sense for it to be in Linux. Let me jump out of the include directory. Was there anything else? Maybe let's look at utils and etc and extensions just to see if we can find some tests. And then we'll jump over to Emacs. Ether types is the only thing in etc. I think this is a file, not a directory, right? Yeah. So what are, okay, Ethernet frame types. Oh, this is interesting. So this is some table. What's the extension? No file extension. So we have BPQ, IPX, PVP, IPv6, and a hex number. And this list is from IANA. All right. So extensions, we have like, I guess, some Mangle stuff for ARP, it looks like. EBT. I'm not sure what EBT is, but these are like IP6 stuff. Maybe these are like rules or types of rules. Some checksum stuff, classify. Okay, there's lots of stuff here. So extension seems at least interesting. Libipq. I'm not sure what, I think IPQ is a general thing, right? Am I just blanking on the, or is this the thing I just looked up with the net filter or the rules manipulations? For packet queuing. For Iptables user space packet queuing. So libipq provides an API for communicating with IPQ. Libipq has been deprecated in favor of the newer libnetfilter queue. Okay. Cool. And then IP4, this seems to be IPv4 and IPv6 stuff. And we have this Linux list header, which is, I'm not going to read without syntax highlighting. Okay, so let's jump over to Emacs. All right, so where do we want to start? Let's start with, I guess, the headers for iptables.h. Shared library should call one of these. So we have do command 4. I don't know what makes it 4. I guess IPv4, which takes an XTC handle, which might be a handler. Bool restore, I guess, whether to restore things maybe after it runs. We've got functions delete chain, flush entries, probably from some queue. The queue does not seem to be passed in, but we get the chain and the handle. And we have these XTC and XT prefixes on things. So XT chain label and XTC handle. And maybe Xtables is supposed to be like a general, maybe X is supposed to mean like a general label or handle as opposed to specifically an IPv4 handle or whatever. I'm not sure. A for each chain function. So this should be some just for each. That's you're gonna pass it in a function and a chain label, an int, but it doesn't tell you what the int is for. Oh, this is still part of the, I guess, the function definition in XTC handle. And then in addition to that function, I guess you're passing in whether to be verbose, built-ins too, I guess whether to do something also with built-ins, and a handle. And you can print a rule. And we've got globals. Okay. So maybe we should look at Iptables internal. See if we can find that. Internal.h. And this doesn't have much. We've got the program. We're going to find the program name and the version and extern int line. Okay. So IP6 tables, I'm going to guess, looks just like IP4 tables, and indeed it does. And maybe the stuff's in, let's look in Linux. The netfilter should be important. I'm just curious to look at kernel.h. So kernel.h contains some often used function prototypes, etc. So these are, I guess, sysinfo. Yeah, these look like system calls, I guess. Uptime, second since boot, total swap, like how much swap space do we have, number of current processes. Okay. Let's look at netfilter.h. And we're going to include Linux types and other Linux stuff and not much else. So not much else from the Iptables / netfilter world, it looks like. And this seems like essentially an enum, but they are defines responses from hook functions. So they can drop, accept, stolen, queue, repeat, stop, or max verdict. I don't know if stolen is supposed to be like work stealing, like you can steal it from another queue, or if it's something more insidious. We have a verdict mask, which we overload the higher bits for encoding auxiliary data, such as a queue number or error values. Not nice, but better than additional function arguments. Okay. Seems like maybe an efficiency optimization. So more stuff about verdicts. So I guess when you apply a rule, you're going to get some sort of verdict, and that has a mask. Extra verdict flags, yeah. NF verdict Q mask. And we've got NFC unknown and NFC altered. And the NF verdict bit should be 8 now, but user space might break if this changes. So it's set to 16. All right. We've got NF. I guess NF should be netfilter. Internet hooks are pre-routing, local in, forward, local out, post-routing, and num hooks. Okay. And then we've got dev hooks like ingress and num hooks. Net dev. Is this like device? Look up net dev ingress. Device name. Does it mean device? I'm gonna guess it means device. Some mailing list stuff. All right. Then we get some enum. I guess protocol. These are protocols: unspecified, internet, IPv4, netdev. Is netdev a protocol? Maybe it's a protocol. Linux namespaces. I'll ask ChatGPT what netdev is. Network device driver and refers to, okay, thank you. So network device driver. I don't know why that's a protocol. Okay, and then we have internet addresses, like whether it's IP is, I guess, big endian 32, IP6 is big endian. IP6 of 4 is big endian 32. And then we also have these structs, like in6 address and in address. Okay. All right. So where's the good stuff? Let's try netfilter. Here we get some of the XT prefix stuff. Let's look at Iptables.h. We have a struct for an entry match. I wonder if I can do, let's see. Hungry delete. Okay. We have a struct for an entry match. We have an entry target, a standard target, an error target. I think targets in let's see, Iptables are like the thing that you do next, like the thing that you're applying after a rule matches. See if we can look up an Iptables cheat sheet of some sort. No, I don't want a big flow. And maybe I do. Means order scheme. There's pre-route. Okay, so I guess mangle pre-routing comes first. I think mangling is like changing, like peeking into the packet and changing stuff. And then NAT pre-routing. And two forwarding process. A mangle forward, filter forward. And then a routing decision is made. And then we have post-routing, mangle, and then NAT post-routing. I guess, so NAT is network address translation, right? So I guess we mangle before we NAT, and then we, when we're pre-routing, and then we NAT after we mangle in post-routing. So these mangle and NAT, I guess, go in the same order rather than being reversed. And then when we go down here, we first mangle input, then we filter input, and then something about local processing. I guess this is like a local process that runs. And then we mangle the output, then we filter the output, and then we NAT the output. And then we get outbound traffic. All right, so that's like how I guess that's the order in which filters are applied. I was looking for something more, more like this. So we have a protocol, I guess options in, out, a source, a destination, and then whatever this thing is, state related. And let's look at make sure that we know what a target is. Targets. A firewall rule specifies criteria for a packet and a target. If the packet does not match, the next rule in the chain is examined. If it does match, then the next rule is specified by the value of the target. Okay, which can be the same as which can be the name of a user-defined chain, or one of the special values except drop, queue, or return. So I don't know what the right metaphor is, but so when you have a rule, you can enter a rule with like, I guess, one of 1, 2, 3, 4, 5 things. One is accept the packet, drop the packet, queue it, or return it. I think return it means to send it back, kind of with like a return to sender. This was rejected or something. Maybe we'll look in a second. And then I'm not sure what queue does. But the other thing that you can do is essentially have a go-to statement to go to another rule that could be user defined. So what is so queue packets with a target of queue will be sent to queue number 0. In this case, I think this is working through an example, but okay. So let's look up queue and return. Okay, return means stop traversing this chain and resume at the next rule. Okay, never mind. Return doesn't mean what I said it did. So return means stop traversing this chain and resume at the next rule in the previous calling chain. So it's like a return function. And if we reach the end of the chain and return is matched, the target specified by the chain policy determines the fate of the packet. The target specified by the chain policy. So I guess there's some chain policy. All right. And what does queue do? Queue means to pass the packet to user space. So it goes to some user space queue. And how it works depends on the queue handler. Okay. Cool. Let's figure out what a chain policy is. So the default policy is accept. Okay, so I guess policy means you. Okay, so accept input forward out in output. So accept seems obvious. Input. I'm not sure what input. The default policy on the input chain to drop. Oh, I guess so it's like the input chain. I don't know what it means as a policy. I guess it means like we'll change the policy for inbound traffic to drop. Okay, so maybe input is like a modifier of the thing that comes after it. So the policy is like input accept or input drop or whatever. All right, that's totally sensible. All right, so let's go back to the code. Okay, so we have xt error target. So the targets, we decided that we know what they are. And what else do we have there? We have entry targets, error targets, some stuff with a line, counters, xt entry iterate continue, match for each. So let's look at the struct for entry match. So what's a match look like? We have a match size. I don't know if that means like what, how much of it matches, or like if it's a regex or something. And we have some stuff for user space, which is a name and I guess a revision. Oh, okay. And this is actually, this struct is called user. So user knows about match size, name, and revision. And the kernel knows about match size and match, which is of type xt match. Then we have the total length and some data. See if we can find xt match. So xt dash match. Okay. So here we have what might be we're going to find IPT match, xt match. All right. I'm not sure what that is. Let's keep poking around. All right. Here we're in iptables / iptables. And let's look at, I guess, iptables.c. We get a copyright statement from 2000 to 2002. I'm not sure, how old is iptables? From 1998. So this is fairly early on in the development of iptables. This particular file, that is. Okay. We have unsupported rev. So I guess that's for in case there's an unsupported revision. And we have original options, original opts. And these are values. I don't know if these are like flags, but the options are things like append, delete, check, insert, replace, list rules, flush, zero, new chain, etc. Okay. Replace rules, flush, delete chain, rename chain, source, destination, in interface, etc. Okay, and then we have some globals, like offset, package version. Okay. All functions starting with parse should succeed, otherwise the program fails. Most routines return pointers to static data that may change between calls to the same or other routines, with a few exceptions. Host to address, parse host network, and parse host network mask return global static data. Okay. Christoph Berkey wants P6 to imply MTCP. Okay. All right. So print match is just going to print some stuff, and it's going to take an xt entry match, an IPT IP, and numeric. I guess the printing is not so interesting, but just to maybe just get a sense of what are these types. Let's maybe take a quick look at it. We're going to get their username and their user revision from the match, which I think this seems to be the same match struct we looked at a few moments ago. And then we're going to look up Ixtables find match. So this seems to be some table lookup. And we're going to look up the name and whatever XTF try load is in null. And if we get a match, we're going to call Xtables find match revision. So we'll look up the revision now. And if we get the revision and empty print, I guess if this is not null, then we're going to call I guess if the print function is not null for whatever this revision is, we're going to call print with IP and M and the numeric argument. Otherwise, if we don't have empty print, but if we have match print, then we'll just call printf with some strings with match name and unsupported revision. Otherwise, if we don't even have that, we're just going to print the match name. And the only difference, I guess, is that we don't we don't print unsupported revision. But unsupported revision is not like a where is it defined? Okay, so it's just a string that says unsupported revision. Cool. All right. You can print the firewall. Let's look at this. I guess this will iterate over some firewall stuff. So we're going to go to an IPT entry, which is called firewall, or FW, which I assume is firewall. So IPT entry. I guess maybe that is the struct for understanding firewalls. We're going to give it a target name, a num, a format, and a handle, an XTC handle. And let's see. We're going to create a target and TG. I don't know why we need both, or how they differ, but TG seems like it might be target. We're going to create an XT entry target, which is just called T. Okay. So if we're not if not IPTC is chain, so where's target name? So we're going to look up the target name in the handle. And if it's not a chain, then we're going to call Xtables find target with try load. Otherwise, if it is a chain, I guess, then we're going to call Xtables find target, XT standard target, and XTF load must succeed. All right, so if we are a chain, then I guess we must succeed. All right. Then we'll call IPT get target on the firewall entry and print some rule details, including the firewall counters, the target name, the IP, I guess the protocol, some flags, flags, maybe inverted flags and format. And okay, so that's print stuff. And what else? We can append an entry given a chain label, which is called a chain, and a firewall, I suppose, and some other stuff in a handle. And I'm guessing that it's going to append the chain to the firewall. So let's see if that's what it does. We're going to iterate over the NS address, NS source addresses, and maybe destination addresses. So we're going to iterate over the source addresses, and then we're going to have this inner loop where we iterate over the destination addresses. And we're going to set FW IP source S adder at index I to the source address. And similarly for masks, And for the destinations at index J, we're going to set the destinations. And if we are verbose, we're going to print some stuff. And then the return is going to be set to iptc append entry chain firewall handle. So firewall, okay. So FW is an entry, and whatever it contains, it looks like we're overriding a bunch of stuff if it's populated, right? So like we're starting at 0, we're iterating at 0, and without checking what's in FW, we're just setting fields on it, right? We're setting IP source S and IP S mask. And then we are appending whatever FW is. So where do we use chain? Is this the first time we use chain? Okay, so I think I had it backwards. So yeah, so FW is the new entry. It's being appended to the chain, I assume. I still don't know what handle does, and then we're going to return the thing that we got by calling append. We can replace an entry, which I expect to be similar, except we're replacing stuff. Yeah, we call iptc replace entry. Insert entry, is that different from add entry? Maybe append entry? I guess we insert it at an index. You give it a chain, an entry, a rule number. This is presumably the index that we added. And so let's see if we can find rule num in the function. Yeah, replace entry with rule number. Insert entry. Again, we get a rule number, so maybe insert means we're going to, instead of overriding what's in the current entry, maybe this means that we're going to insert this at that particular index, and then bump everything down. And then we can delete an entry. All right, this is starting to make sense. We can check an entry. I'm guessing based on the other functions that ultimately we're calling out to iptc something or other check entry, iptc check entry. And then this for each loopy thing, we can flush entries. All right, so it seems like the real stuff is done, what is it, iptc. Let's look at includes. Maybe, is it Iptables? Or I guess I could just grep for, what directory am I in? Maybe flush entry. So libiptc.h. This looks promising. Okay, so here's at least the prototypes for these functions. Does this chain exist? We can take a snapshot of the rules, returns null or on error. We can free. We can run through the chain, first chain, next chain. First rule, okay. So let's look at some of these implementations. So where do we think this is? So we're in include. So it must be in libiptc, right? And I guess maybe we'll look at the IPv4 ones. So this is looking more like real code. Let's find append entry. So we get some defines. TC dump entries, TC is chain, etc. What? We're defining TC append entry as IPTC append entry. But where is the actual definition? Here's a bunch of defines. You get dump entry. Something about unconditional. What about if we just look for append? Okay. Maybe not. You have things like check match, check entry. Okay. So maybe it's not in libip4 TC. Maybe libiptc. Here we go. TC append entry. We're going to append entry FW to chain, equivalent to insert with rule num equals length of chain. All right. So we get a chain label and a struct entry and an XTC handle. We're creating a chain head and a rule head. we're going to set the function to tc append entry. We're going to try to find the label given the chain and the handle. And then we're going to, I guess, try to allocate a rule. And then do some mem copy from, I guess, of the entry using the offset. And IPTCZ map target handle R, unable to map target of rule for chain. Maybe this is setting, checking that when you have a target, that's the next rule that you're supposed to go to. Maybe map target is trying to just verify that the thing you're telling it to go to exists. I'm not sure. And then you're going to list add tail. The what is R? So R is the rule head and C is the chain head. So we're going to take the rules on the chain and add the rule head list to it. Then we're going to increment the number of rules because we've added one. And then we're going to tell the handle that something changed, set changed on handle. Okay, that's beginning to seem like it's doing some sensible work. I would like to find XTC handle. And I'm doubting it. Oh, here, it is defined here. So here, it's a struct. It's got a sock FD, presumably a socket file descriptor. Whether changes have been made. A list head of chains. So I guess essentially a list of chains since we can walk from the head, presumably. A chain head. A chain iterator current. I guess an iterator into the chain that might be, it's called head, but it's also called current. So maybe it's thinking of it as the head of the current sublist or something. But this seems like an iterator maybe that's where we are currently in our iteration is my guess. In a rule head. How many chains we have. Whatever XTC handle is, it's something that has multiple chains. Yeah. And then we have a chain index array for the fast chain list access. Okay, maybe some sort of optimization for fast access. Change index size and sorted offsets. If chains are received sorted from kernel, then the offsets are also sorted. Says if it's possible to b-search offsets using chain index. Okay, so if we have sorted offsets, which is an int, then we can use binary search. I guess because kernel guarantees that the offsets are also sorted. And then we have an info substruct and some entries, which are struct get entries. I'm not sure what this is. Maybe this is kind of like a getter or setter. These are constants or maybe macros. Struct get info. Okay, let's see if we can find struct get info. Change this to yeah, so we've defined struct get info here, which is IPT get info. All right. Cool. Maybe we'll look for IPT get info as well. What does IPT get info? So it's some struct. Here's another, that's the thing I just saw. And it has a name, which table, okay. Valid hooks, which the kernel fills in. Hook entry points, 1 per net filter hook. Underflow points, something about underflowing. Number of entries in size. It seems we seem to have a few interesting structs here. So IPT replace, so which table, Some more valid hooks, num entry size, hook entry, underflow. Wait, what? More entries. Is this for, I guess, yeah. Okay. That seems like that was supposed to be for replacing stuff, but it seems like it has essentially the same fields as the other one. Okay. All right, so what do we've seen what a handle does. And we have a sense of what the firewall rules are and what's going on with the chains. There should be some code where we push things down into the kernel. I don't think we've seen that necessarily yet, but that should be in maybe Linux. Let's see, kernel.h. I think we looked at this. These are syscalls, but let's see if we can find outside of include. Maybe under lib Iptables. I think at least a quick look at Iptables.c. We need this for IP6 tables restore. Basic exit error, Iptables globals, Iptables free opts, merge options. Let's look up Iptables on the internet. So Iptables are the versions of, are versions of IP tables that use the netfilter API. This is a set of tools to help the system administrator migrate the rule set from IP tables, IP6 tables, ARP tables, and EB tables to NF tables. Okay, so this is like the, I guess, backwards compatibility stuff. Is there anything we want to look at here? Print stuff. It's not so interesting. Parse MAC and mask. This is just some parsing functions for MAC address and maybe netmask. Here's some structured protocols. You can save string. Where are we saving it though? F puts, I guess, to standard out. We're passing a value. There's some escape stuff, some no quote stuff, length, string span. We're going to put character in F puts to standard out. I'm not sure what we're saving. Oh, we're calling F write, but again, to standard out. I'm not sure. Seems like we're doing everything to standard out, but maybe I'm missing something. And then there's some parsing logic. Okay. And a lot of translation stuff, like translating to IPv6 stuff, parsing IPs. Okay, so that's the sort of stuff that's in Iptables.c. And that's Iptables is like the compatibility layer between IP tables and the, what is it called? NF tables, the more recent ones. Let's see if there's anything else here. So there's ARP stuff. I'm going to ignore IPv6 and ARP just because I expect it to be more of the same. I don't know if you look at nft.c. We are importing lots of stuff, including Linux netfilter. We've got some sort of NFT function. MNL talk. I think an NFT handle. And I have no idea what any of these variables. And NLMSGHDR. This is probably the most inscrutable variable name I've come across so far. NLMSGHDR. Header, probably. N maybe is netfilter. NLM. I don't know where to stop parsing. SG source something header. Do you have a? I don't know. MN, and then we have MNL, which is different from NLM. I'm wondering, are these related? And am I supposed to infer something from this naming convention? I'm not sure, but we have MNL socket send to, and we're going to send stuff based on the stuff that was passed in, like NLH message length. Okay. And so we're getting socket stuff. So this should be ultimately calling out to the kernel. MLN, MNL. Yeah, I don't know. Okay. Let me see if Iptables MNL. Does that return anything? Yes, include my search terms, please. I think even if I do that, DuckDuckGo is not going to include my search terms. Okay. Yeah, I don't know. Lib MNL. There seems to be a lib. See if we can find it. Minimal. LibNML is a minimalistic user space library oriented to netlink developers. There are a lot of common tasks in parsing, validating, constructing of both the netlink header and TLVs that are repetitive and easy to get wrong. Okay, so something about netlink, minimal netlink, I suppose, and that's why minimal netlink and then netlink message header. Yeah, there we go. Okay, so something about netlink. Cool. Let's look at NFT assert table. Wait, is tainted. So we're gonna to check if a table is tainted, we're gonna get it an NFT handle and a table, which is a car star, so essentially a string. And then we're gonna call NFT table built-in find and get in the built-in table. And then if we have T, so I guess if we found it, we'll look up the cache and then the table in the cache, passing in the type and looking at its tainted flag. If we didn't find it, we'll return false. So we're not actually doing any work. We're just looking up a value in a struct ultimately. And so what we haven't done yet is looked at one of these find functions. So let's see if we can go to, I don't think there's a whole find file, but maybe Iptables. Yeah, let's do Xtables find match. And let's grep for it. Cool. I'm gonna guess that this is the definition. Yeah, here we go. So we're gonna return an Xtables match, which I think we saw the struct for. And we're gonna pass it in a name, some enum about whether we should try to load it. And I guess an array of Xtables rule matches. And rule matches. Maybe these are rules to match. So we're giving it a name, whether to reload, and this must be the thing that we're trying to match, I guess, right? No. I don't want to find match, I don't think. Let's see what else we have. Find match revision, find target. I want to target now that I think about it. So we're giving it a name and this try load stuff. And we're creating some pointers, previous D pointer, maybe double pointer and pointer. Okay. And we're going to have, this is kind of like a classic search thing. And we have like Booleans about whether we've seen something or whether it's been found before. And if it's a standard target, here's the case logic for if it's a standard target. In that case, we're going to string compare the name against the empty string. And if that succeeds, or if a bunch of this other stuff is true, like if the label is accept or drop Oh. If the name is like accept, drop, queue, or return, one of the built-in things, then we're going to say that it's standard. I guess the empty name is also a standard rule. If it's a known target, so we're going to do not no targets. Oh, sorry, non-target, known non-target. So we're going to call not targets hlist lookup of the name with load must succeed. And you don't have to succeed. I guess we'll return null. So this is essentially if it's a non-target, this we'll look it up in the non-target list, I guess is what it's saying. Otherwise, we're going to trigger delayed initialization. And we're going to set the D pointer to pending targets, whatever Ixtables pending targets is. And then in the for loop, we're going to increment the D pointer. And we're going to check if we're going to do extension compare of the name and the D pointer name and the D pointer family. So we're essentially comparing the name with what's in D pointer. I don't know really what the D pointer family does. And if that succeeds, we're going to set pointer to D pointer, and D pointer is going to go to next. And we're going to say that we've seen it. Seen what? I don't know, but seen is set to true. And if we haven't found it, and Ixtables fully register pending target pointer prev, then we'll set found to true, set prev to pointer and continue. This, I guess, reiterates through the loop. Else, if previous, I guess, is non-null, we'll continue. And then either way, we set D pointer to pointer, and D pointer goes to D pointer next. Okay, wait. So if this thing matches, then we set D pointer to pointer. But if it doesn't match, we just set it to next. And either way, we like fall through to this condition, I guess. So what is this doing? So fully register pending target. If we haven't found it, and fully register pending target with pointer and previous is true, I guess, then we found it. I don't know why this means that we found it. Maybe we can find this function. If we've seen it and we haven't found it, then we say extension is not supported, missing kernel module. Maybe this is somehow a test of whether some kernel module is here. Trigger delayed initialization. Maybe we don't load it into the kernel until somebody asks for it. Somebody checks that it exists. That might be what's going on, and that would be why we could get a register function here. And so if we have seen it and didn't found it, then really found, I guess, means like registration successful or something like that. If my theory is correct, then we'll say that extension is not supported and we're missing the kernel module. Okay, so if we're down here, then then it's not the case that we've seen and not found it. So I'm not sure whether we've seen it or not, but at any rate, we set pointer to Ixtables targets, and then we're going to, I guess, this is a for loop. We're going to iterate over the pointer. We're just going to crawl across the linked list using the targets, and we'll call extension compare of the name, the pointer family, etc. And something about cloning. First target the type, second and subsequent clones. Yeah, I'm not sure why we're cloning. And then some stuff about no shared libs. If pointer and not try load is equal to don't load, etc. And now we're doing some stuff. And then various conditions on try loaded. If try load is not equal to xtf don't load, then we'll say pointer loaded is equal to 1. Otherwise, we'll set pointer to null. If we tell it not to load, I guess we'll set pointer to null. And maybe load means like register. in this sense. I don't know. I'm not sure exactly what load means, but if we're down here, haven't we already tried to register it? I don't know. And if pointer is not null, then pointer used is going to get set to 1. Otherwise, no targets. Otherwise, we're inserting it into the list of known non-targets. And we're returning pointer. Okay, so I'm not entirely sure what's going on here. Let's look up try load. I think this is like lazy loading. Wait, Iptables try load, right? Yeah. Maybe try Iptables lazy load. Let's try ChatGPT. Does Iptables lazily what did they call it here? Delayed. Okay. Maybe let's try delayed initialization instead of lazy load. So what is delayed initialization in Iptables? Something went wrong. Oh, bummer. The feature in the Linux kernel's packet filtering framework that allows administrators to defer the activation of rules in Iptables until after the network interface has been fully initialized. By default, Iptables applies rules as soon as they are loaded, which can sometimes cause problems if the network interface isn't fully initialized. For example, if a rule references a network interface that hasn't been created yet, the rule will fail. Delayed initialization helps to avoid these problems by postponing the activation of rules until the network interface is ready. This is accomplished by using a special target in Iptables called delay that tells the kernel to delay the processing of the rule until a specified event. Okay. But I don't see any explicit call to delay. So, figure delayed initialization. Let's look at this function. I don't see anything that seems to branch on like some setting or even what's passed in. So it's hard to say. Okay, but more now. Fully register pending match. Let's grab. I thought I grabbed the string. Okay, so static bool Iptables fully register pending match in Iptables. Fully register match target, which was previously partially registered. Okay. Where's the implementation? This is in the C file. Here's the implementation. Okay, so we're going to fully register pending match. We're going to give it a match. ME, I guess me in the previous one. We're going to create an Iptables match, which is I. It seems like it's going to be an index, and a r star called rn. I guess real name. See if a new match can be used. So I guess we'll look at the real name and check if it's null. Sorry, if it's not null. If it's not null, then we'll use its real name. Otherwise, you'll use its name. And then we check if compatible match revision. And if not previous, so if the second argument to the function is null, we'll append it to the list. Otherwise, we're going to set this temporary variable to be the thing that was after previous, and we'll set previous to be its own next. Okay. And then we'll set the next of me to previous, and set I to me, and set me m to null and m flags to 0. So I was a little bit, this should be standard like list insert. So, okay, so we're going to register pending match, fully register pending match. So this is inserting it in the list, but what I don't see is where so it's going in an Iptables match. So all we're doing is changing the Iptables match list, right? So there's nothing like a call to anything like a kernel. So what makes it partially registered? I don't know. And then fully registering it, I guess, just adds it to the list. Here's Iptable register matches, which takes a match and an n, and we're just going to iterate up to n and register the match at I. So we're going to register all of the matches in this thing. Let's look at Iptables register match. We've got, okay, so to register a match, we're going to give it a match, and we're going to initialize this position pointer. And whether I've seen myself, which is false. If if there's stuff after me, then we're going to say you're already registered. We already know about you because you have stuff after you, I guess. If my version is null, then we're going to error out with missing version. Check size. We're going to check alignment. Do more error checking. Yeah. So maybe this is what it means by partially. We've done the error checking. I guess, validate some options. So order into linked list of matches pending full registration. So we're going to set the, I guess, position pointer to Iptables pending matches, which is not passed in, right? This is just something, I guess, in the scope. Okay. So I guess being pending just means that you are on a different list, right? Or you're in some structure of pending matches. And we're going to iterate over the list and use string compare and whatever family is, and check whether we've seen ourselves. The group by name and family. So if string compare me name blah, blah, blah family, if that succeeds and I've seen myself, we're going to break. If I haven't seen myself, we're going to continue. And if we're here, then we've seen ourselves, I guess. And we'll check if we match prefer me position. And if so, break. Put preferred items first in group. So somehow there's a notion of a preferred item, and they go in the beginning of a group. And if our own group was not found, then, and I guess if the position pointer is non-null and I haven't seen myself, then we'll set position to Iptables pending matches. We'll set the next of me to position. I guess that makes me first. that right? If I so whatever the stuff in the pending matches is, I seem to go at the beginning here, and then we set position to me. The position is now the beginning of the list, and I am at the beginning, I think. And then we're going to print some stuff if there's debug. Okay, so that's just list manipulation, and we have this pending matches thing. Keep track of matches targets pending full registration. Linked lists. Yeah, they certainly are. Okay, and so what is a match? Did we look at that table match? What's it called? Iptables match. Oops. So, yeah. Let's see if we can find the Iptables match struct. Maybe like this. Maybe at the beginning of a line. Looks promising. Include file for additions, new matches, and targets. I can't remember if this is what we looked at before, but the ABI API version of this module requires must be first member, as the rest of the struct may be subject to ABI changes. Okay, so you keep track of the version. If the version changes, other things might change. We're a linked list, yeah. We've got a name and a real name. A revision of the match. I guess this is if you change things. The revision might be bumped. Extension flags, family, which is just a uint16. The size of the match, user space size, function which prints out a usage message, initialize the match. So we get, I guess, some initializer. Function which parses command options, returns true if it ate an option. Entry is a struct IPT entry, for example. So parse, yeah. Final check, exit if not okay. So we've got a function to print out the match if and only if it's non-null. Put space at the end. Something to save match info into a parsable form to stand it out. Okay, I guess that's what it means by save does seem to just print to stand it out. You can print a match name or alias. And we have a pointer or struct to command line options. Some more parsing stuff. We can translate a function to translate IP tables into NFT. Size of per extension instance. And some stuff that we're being told to ignore, like simulating loading. That's a lot of stuff. This is essentially a class in the C++ sense because we've got both a struct, but we've also got these like function pointers. So this is a thing that has both state and behavior. And this is what a match is. So a match should be, okay. And yeah. Family. Is family address family? Protocol family dependent information. Iptables AF info. Kmod, maybe kernel mod proc exists, process exists, the prefix family IP proto match and target. Okay, so I'm going to stop there. Mostly in the interest of time. I think I'm, so this is certainly not something I understand fully yet, but I'm beginning to get a sense of what's going on. So we've got these matches, which are these linked lists, and we're going to register them into chains. And I'm going to guess that family includes information like protocol family, like are we doing TCP or UDP or something like that? And these matches will contain the information that the kernel is going to use to match individual packets. And then, actually, as I'm explaining this, let's was it Iptables match? And also extensions. And so as as the things are matched, we also have these functions for like callbacks of various sorts. Including some parsing stuff. X6 is probably IPv6, and we have logic how to translate the match into NFT, which is I think close, which should be closer to what the kernel understands. And so this should be the key struct. And so essentially it's a linked list of matches. And there's also this notion of a chain. So I guess before I go, let's do two things. Let's figure out what a chain is as a type. And let's look quickly at Ixtable's target. So this should be essentially like a go-to to another match or another chain. I'm not sure at which level of granularity. So a target has a version. It's also a linked list. It's got a name and a real name. The real target behind this, if any. Okay. It's also got a revision, some extension flags, and a family. We could print stuff out. We can initialize the target. Here, we have this parsing function, final check function alias, new parser stuff, translate into NFT, and size. We have a rule match. A rule match has a linked list structure and contains a match, and whether it's completed. Multiple matches of the same type, the ones before the current one are completed from parsing point of view. I don't know what makes this a rule. It seems to just kind of be a wrapper around a match. This is basically overhead to give it a list structure, and then it's got a Boolean for whether it's completed. But what I wanted to know is like, so where in target we should see something like, it should point to something that can execute, right? Is this one of the functions? So we can initialize the target. Maybe it's handled in the functions. See xt entry target. See if we can find xt entry target. We have add target. Is xt entry target a struct? It might be. Wait, no, hang on. Wait a minute. This is interesting. Xt option call. Xt option entry. Whatever xt option call is, it's got so some option thing. It's got flags, and it's got a union of matches or struct. Wished for a world where the ones below are gone. Okay. Yeah. Oh, so this is just a type. I thought this was the name of a function I could look up, but this is just some init function that that you can pass in. Okay. It's an Ixtables target. Yeah. So I don't have a full understanding, but I'm at least beginning to get a picture. So let's see if we can find stuff about chains. We can announce a chain. Let's try chain. We have NFT command. That looks promising. Lib NFT NL. Do this NFTNL chain.h. That extract NFT chain. That's a function that returns an NFT chain. Maybe if we do look for struct NFT chain. What is me about my okay. So here's NFT chain.c. Let's look at that. Oh wait, no, let's not look at that. Here's the chain. Okay, so an NFT chain has a list head, an HList node, an NFT chain. This is the thing that makes it a list, and an NFT NL chain. An NFT chain list has a list head and an HList head. What is an HList? I don't know. Let me try, instead of using Emacs for grep, let me try grabbing on the command line. So, recursively. So nft.h maybe? No? These are operations with tables, but it doesn't seem to really define them as anything. And they don't seem to be defined anywhere else. See if there's other appearances of NFTL chain, NFT NL chain. We can alloc them and free them. I'm not sure. Let's look at NFT chain in general. We're including the header. Okay, so we can alloc a chain. That's just calling Iptables malloc. We can free one, etc. Okay, more alloc. We can delete and free. And then maybe it includes. Not sure. I think maybe this is stuff that, it's possible this is stuff in another repo. Let's try this function one more time. Was it NFT chain? Including NFT chain.h. Is that here? That is here? Yeah. Okay, so this is the thing we just looked at. And we're including lib nftnl. And I think that let's see. Yeah, I think the reason I'm not finding it is because it's in the NFT repo, which makes sense. Okay, so ultimately we're like bottoming out at the NFT stuff, which was expected when we when we entered into this enterprise in the first place. And that makes sense. And so is there anything else that's a mystery? I think we looked at the handle. A chain is basically a linked list of stuff. I don't know if we know what HList is. Maybe we can find HList. HList node. Maybe struct HList. We have heads. Maybe HList and then just grep for, see if it's a define. Define HList head name, struct HList head. I guess HList head is probably as good as HList. The Linux list, where is it? Lib IPTC. Okay. Container of. Here we go. HList head, double linked list with single pointer list head. Mostly useful for hash tables where the 2-pointer list head is too wasteful. You lose the ability to access the tail in O of 1. Okay, so it's just a hash list. All right. I figured it was good to kind of just double check some stuff. Okay, so that's, at the end of the day, everything is really simple, which is not surprising because it's the job of IP tables to create lists of rules and pass them off to the kernel. And because of the way that that we're ultimately using NF tables, there's also, I think, this additional library where things will first get converted into NF tables, and then NF tables will pass things on into the kernel, and that's how things go. So that's IP tables. And in the next couple of days or so, I'll put up my schedule for next week. There's some exciting things planned. I'm not sure what I'm able to announce this week, but certainly we'll have the schedule. And then in the next couple of weeks, I'll be maybe trying some new stuff. So that's all for me. Thanks for watching.